Let us continue our discussion on the modes of heat transfer. After conduction, the next important mode of heat transfer is convection. So when we are taking a hot cup of tea, then we all have experienced that if you wish to take the tea in a leisured manner, you allow the tea to get cooled on its own. So slowly the hot tea interacts with the environment and then slowly gets cooled, and then you enjoy the tea as it becomes comfortable in temperature. So the hot tea is losing its temperature, hot tea is losing its heat to the environment by natural convection in that case. But suppose you are in a hurry and then you want to finish the hot tea fast. What obviously you will do? You will blow the air over a tea and then try to cool the tea fast. So in that case also tea loses its heat by convection, but in a forced manner with your blow of air. When you are blowing air, you are making it forced convection. You are cooling the tea with forced convection. So convection heat transfer needs some media for transfer. It is a heat transfer across the media. So it is a heat transfer by molecules through some media like fluid or gases. Heat transfer from a hot or cold surface to a cold or hot gas or fluid, it takes place by convection. So it is the convection is not restricted to like conduction. It is not restricted to a homogeneous material. So it is across some media heat is transferred. So some examples, there are two types of convection modes. One is forced natural convection and second is forced convection. Now these are some examples of natural convection and forced convection which we encounter or which we experience in our day-to-day life. You all have seen the Pepsi kiosks. These Pepsi kiosks, these are refrigerators, so freezers in which these bottles have been kept. Now these bottles are kept and these bottles become cool. How do they are cooled? They are cooled by natural convection. They are kept in a cold air environment, and the cold air environment slowly absorbs the heat from the cold drink and then it becomes cool. This is one example of natural convection. Heat is removed by natural convection from the fluid. In this case, in all industrial hot water generators, now this is the case of forced convection. So burners, this is an industrial hot water generator in which hot water up to 130 or 150 degrees Celsius is generated. Here burners, they burn the gas and then the gas is burned here. Hot air is generated. This hot air transfers the heat to the net of the tubes. In these tubes, hot water is circulated. So hot air transfers the heat to the net of the tubes or coil of the tubes here by convection. But this is forced convection. Here there is a fan placed and then it becomes a forced convection case. So this is a natural convection example and this is a forced convection example. To go further, another example of natural convection is that we all know immersion heaters. So immersion type of heaters, when you dip into a container, dip into a bucket and then switch on the heater, then this surface becomes hot by electricity. Then this surface transfer heat to the water in the bucket by natural convection and water becomes hot. So this is again the most usual or normal domestic example of natural convection. Another case of forced convection is that when you dry the hair with a hair dryer, a blow of warm air is blown from this dryer and then you will receive the hair receives the heat and then they become dry. Okay, so this is the air is forced from the dryer and it is forced convection heat transfer which is taking place. Again, this is an example of forced convection. This is a radiator type of heat exchanger. Some fluid, some hot or cold fluid is entering For example, say cold fluid, cold water at 1 degree or 2 degrees Celsius is entering into this radiator. These are the radiator fins. Okay, and then these fans are forcing the air over the surface of these fins, so air becomes cool. In all the air handling units in air conditioners, these type of radiators are used where cool air is needed. So here air is forced over the fins of the radiator fan. This becomes a case of forced convection heat transfer. Another natural convection heat transfer natural convection heat transfer example is sun is radiating heat on this pond, and then this pond is getting heated by convection. So water gets heated up in a pond with natural convection. So hot portion it remains upper convection zone. So convection currents are set up in this. So this is a case of a natural convection heating of a pond. So with these examples, let us turn to the equation. So the governing equation of convection is called Newton's law of cooling. So Newton's law of cooling says that Q, rate of heat transfer, is equal to H, convective heat transfer coefficient, HA. A is the surface area, and then Ts is the surface temperature, and T infinity is the surrounding temperature. And then this the entire equation is the Q is expressed in watt. For example, if we apply this equation to here, this case is the with the a pot or a pan is kept on a gas flame here. These are the flames. So here, what is the rate of heat transfer by convection? So this water is getting heated. Okay, so this becomes the area of heat transfer. So area across which heat is transferred. Ts is the surface temperature of this pan, and then T infinity is the temperature of the fluid. Okay, this is being heated. So the higher is the Q, the quicker water is getting heated. So this convective heat transfer coefficient H depends upon geometry, lot of factors: geometry, orientation, velocity, pressure, density, viscosity, temperature of the surface, as well as surrounding fluid temperature, buoyancy. So this convective heat transfer coefficient is a very vital parameter to be determined in case of forced and natural convection. So this is the main parameter which is to be determined usually. Now what is the unit of this convective heat transfer coefficient? It is watt per meter square Kelvin. This you will obtain when you when you shift all these parameters here and obtain an expression for H. So H is equal to watt per meter square per Kelvin. The most usual case of convective heat transfer is hot fluid or gas flowing through a pipe, insulated or not insulated. So you can say that this is a pipe through which hot fluid is flowing. So this hot fluid is giving its heat to the pipe surface. So pipe is becoming hot. So the pipe gets heated due to convection. So hot fluid flowing through the pipe of length L imparts the heat by convection. So heat is transferred to pipe surface in this case by forced convection, because water is not steady here, water is moving with certain velocity. So it is a case of forced convection. So then by Newton's law, what is the equation here? Q is equal to HI AI. So heat is transferred from inside. So HI AI. AI is the inner surface area, and T infinity minus Ts. T infinity is the hot fluid temperature, T infinity, and Ts is the temperature of the inner surface temperature of the pipe. This is again in watt. In the above expression, for evaluation of Q, the parameters except HI are known. So we need to evaluate Q, and then we generally know AI and we generally know the temperature difference. HI is not known. So the question here is how to estimate the convective heat transfer coefficient HI for inside. Now in the above expression, HI is the convective or film heat transfer coefficient from inner fluid to inner pipe surface. So fluid to inner pipe surface, HI. So in that case, area under consideration will also be AI. So AI represents 2 pi Ri into L. If L is the length of the pipe, then 2 pi Ri L is the inner area. Similarly, so here the direction of heat transfer is from hot fluid to the inner surface of the pipe and then towards the outer surface of the pipe. From inner surface to outer surface, heat will be transferred by conduction, and then from outer surface again heat will be transferred to the ambient by convection. So here, if the pipe is not insulated, for example, let us say the pipe is not insulated, it will lose heat to the ambient by convection only. In that case, we can calculate the rate of heat transfer to be equal to HO AO. Now HO is the heat transfer convective or film heat transfer coefficient from the outer pipe surface to the ambient. Okay, and then AO is the outer area. So this is 2 pi RO. So this is RO. So 2 pi RO into L. Now again the same question we need to solve, how to determine the value of HO. A very brief discussion of how generally in such cases of pipe or fluid pipe flow, how convective heat transfer coefficient is determined. This is a very elementary discussion of how it is determined. So it is generally determined in a non-dimensional fashion. So here Nusselt, this is Nu is the Nusselt number, which is equal to C is a constant, Re raised to A, Re is the Reynolds number. So Reynolds number raised to A into Prandtl number raised to B. So this equation is, so these constants are determined by experimental or empirical relations. So this is the famous Dittus-Boelter. This equation is called Dittus-Boelter equation. So Nusselt number is given by this expression Hd by K, in which H is the convective heat transfer coefficient, D is the characteristic dimension, and K is the thermal conductivity of the fluid. Rho is the density of the fluid, V is the velocity of the fluid, D is again characteristic dimension. Mu is the dynamic viscosity of the fluid. So here it is Newton meter per second square. And then Cp, Prandtl number is given by mu Cp by K. This is the expression of the Prandtl number. These are all dimensionless numbers. So this expression is a dimensionless expression. In this generally Reynolds number is determined, Prandtl number is determined. So by knowing Reynolds number and Prandtl number, for a certain situation the values of C, A and B are known. So the only unknown will be Nusselt number. You evaluate Nusselt number. In Nusselt number, characteristic dimension is known and thermal conductivity of fluid is known. So you can calculate H. That's how the convective heat transfer coefficient is generally determined. Now combined conduction and convection. So consider the case of a hot fluid flowing, again the similar case in which hot fluid is flowing through an insulated pipe. If the pipe is insulated here, so this is a hot fluid, this is a pipe, and then over which the insulation is placed and over which cladding is there. Now let Hi be the convective heat transfer coefficient from the fluid to pipe inner surface. So Hi is the inner film heat transfer coefficient. Ho is for outer surface, convective heat transfer coefficient from cladding surface to ambient. Ta, let Ta be the ambient temperature. Tf is the hot fluid temperature. Then T1 be the temperature of the inner surface of the pipe. So this is the T1 is the inner surface temperature of the pipe. Then T2 be the temperature of the outer surface of the pipe. So this is T2. Okay, and then this becomes T3. T3 be the temperature of the outer surface of the insulation. So this is the outer surface of the insulation. We assume the thickness of the cladding to be very less. So cladding is very thin. So we neglect the thickness of the cladding, and then we assume that the T3, that whatever outer surface temperature of the insulation is the same temperature of the cladding. So cladding and outer surface, the insulation is in thermal equilibrium with each other. So now what is the direction of heat transfer? Heat Q is convected from hot fluid to the pipe inner surface. Okay, so first from hot fluid to pipe inner surface. Then heat is convected from this point till this point. Now from pipe inner surface to pipe outer surface, heat is conducted. Okay, so we know the thermal conductivity of the pipe. Then from pipe outer surface to the insulation outer surface, heat is again conducted. And then from insulation outer surface, heat is convected into the atmosphere. So this is how the heat is transferred. Now we have to write an equation for the calculation of heat transfer. If we apply Fourier equation or we apply Newton's law of cooling for this convection, then Fourier's equation for this portion, Fourier's equation for this portion, and then again Newton's law of cooling for this portion. So if you applying Newton's law to each section of material, Newton's law of cooling, so we can write down first. So how heat is transferred? By convection. So AI HI or HI AI into T infinity minus T1. So HI AI T fluid minus T1. So same heat is being transferred. So here conduction for cylindrical surfaces. So what is that? T1 minus T2 by natural log of R2 by R1 2 pi KCl. So we already know this equation. So heat is conducted over this surface. Now again heat is conducted over this surface. So we are applying Fourier's law for cylindrical sections. T2 minus T3 by natural log of R3 by R2 2 pi KIL. Ki is the thermal conductivity of insulation. Here thermal conductivity of pipe. Okay, which is equal to heat convected out to the atmosphere. So HOAO T3 minus TA. So this is all equal. Okay, heat transfer remains the rate of heat transfer is the same. So if we simplify this and write it in this format, you will get TF minus T1 by this simplification, and this quantity comes in the denominator. Again, if you further simplify in a format of potential difference, like TF minus TA, if you just go on adding all this and then combine all this by addendum. So TF minus T1, this minus T1 adds to plus T1. So this T1 gets cancelled. Then minus T2 plus T2 gets cancelled. And minus T3 plus T3 gets cancelled. So finally you get TF minus TA. So TF minus TA is equal to all this expression 1 by HIAI plus log of R2 by R1 2 pi Kp is the thermal conductivity of pipe, Kpl plus log of R3 by R2 2 pi KIL plus 1 by HOAO. Okay, then if we consider unit length of the pipe, then L becomes equal to 1. Okay, and then on the basis of inner diameter of the pipe, AI is 2 pi Ri. AI is a 2 pi Ri. So we obtain Q is equal to AI. So this expression is for Q. Now Q is equal to AI TF minus TA 1 by HI plus. So this is the expression. If we model this equation as an overall heat transfer coefficient, then this AI and TF minus TA remain the same. So AI and TF minus TA remain the same. So this UI represents this part of the equation. So AI and TF minus TA, they are cancelled, and UA, you get an expression for overall heat transfer coefficient in the combined conduction and convection mode. So UI is equal to 1 upon 1 by of course on the basis of inner surface area. Okay, so on the basis of inner surface area, overall heat transfer coefficient UI is equal to 1 upon 1 by HI plus AI into log of R2 by R1 by Kp plus AI log of R3 by R2 upon Ki plus AI by HO and then 1 by HO. So this will give you the overall heat transfer coefficient. Similarly, on the basis of outer diameter of the composite section, AO, where AO is represented by 2 pi RO, in most of the cases we know this figure only. So in the most usual way of calculating overall heat transfer coefficient is this UO is equal to 1 by AO by AIHI plus AO into log of R2 by R1 by Kp, thermal conductivity of the pipe, plus AO again into log of R3 by R2, this is for insulation, and then plus 1 by HO. You can, if the number of sections are added, then you can go on adding this, and then last term will be the convective term. So this is the combined conduction convection cases. So let us attempt some practice examples, and then we'll get an idea. This is the first problem, in which reads, a steel pipe is covered with 25 mm insulation having Ki equal to 60, and the outside of the insulation is exposed to an environment having H equal to 10 volt. TA is 20 degrees Celsius and the temperature of the inside of the pipe is 250 degrees Celsius. So for unit length of the pipe, calculate overall thermal resistance and heat loss. So pipe dimensions are as follows. ID of the pipe is given as this, and then thickness is given 7.6, and then thermal conductivity of the pipe is given as 54.5. So this is the arrangement, this is the pipe, and this is the insulation. So we need to calculate overall thermal resistance and then rate of heat transfer. Now our nomenclature will be like this. This is the inner diameter, inner radius of the pipe is R1, and then outer radius of the pipe is R2, then outer radius of the insulation is R3, ambient is given, HO, heat convective heat transfer coefficient outside is given. So the thermal conductivity of the pipe is also known to us. So this is R1, R2 is given, R3, KP, KI, HO is given, TA is given, and T1 temperature to 250 degrees Celsius of fluid, inlet fluid is given. So inside pipe has a 250 degrees Celsius temperature. Now overall thermal resistance is equal to overall reciprocal of overall heat transfer coefficient. So R is equal to 1 by U. So as outside convective heat transfer coefficient is given, we will write an expression of overall heat transfer coefficient on the basis of outer surface area of the composite section. So using the expression of overall heat transfer coefficient for composite cylinders, which we have previously used here, so this expression we will use. Okay, so if we use this expression and then substitute the values, so you can go through these values, how these values are substituted. So this is for pipe, this is for insulation. As HI is not given, here HI is not taken. Okay, so HI is not taken here. So UO, if you calculate, you will get the value of UO to be 1 divided by 3.342. So that is 0.3. So value of U is 0.3. So overall resistance is reciprocal of that. So that is 3.34. So the unit of resistance is also reciprocal of the unit of overall heat transfer coefficient. So the unit of overall heat transfer coefficient is meter square Kelvin, so watt per meter square Kelvin. So the overall thermal resistance is expressed in meter square Kelvin per watt. Now from this you can calculate the overall heat transfer coefficient. So UA delta T. So U0 is 0.3, which we have calculated. A0 we have calculated here, I think. Yeah, A0 is 0.436 calculated, and then 250 minus 20 is the delta T. So Q comes out to be 30 watt per meter. Now this is per meter. So this is the simple case of conduction convection. Now next problem reads, water flows through the inside of the steel pipe with an ID of 2.5 centimeters. So this ID R1 is given, and the thickness of the pipe is also given. The wall thickness is 2 mm. So R2 is also given. And the convection coefficient on the inside is 500 watt per meter square Kelvin. Okay, so inside HI is given here. The convection coefficient on the outside is 12 watt per meter square Kelvin. So outside is also, HO is also given. So HI and HO are given. Calculate the overall heat transfer coefficient U, and then what is the main determining factor for U. So this is a very simple case of HI and HO. So again R1 is given, R2. So R1 is given, R2 is given, HI is given, and HO is given. So we will apply again the same equation of UO. So here HI will come into picture now. So 1 upon AO by AI into HI plus AO. This is a pipe. This is for R2 by R1 upon KP is the pipe section, and this is for HO. So if you substitute all the values here, you will get the value of UO, overall heat transfer coefficient, to be 12.11 watt per meter square Kelvin. Now in this, why it is written here? Because we need to determine which contributes in this UO, which factor is contributing in a major manner. So you can just, if you just have a look at these figures, this is 0.08, which is because of the outer heat transfer coefficient. this second, because of the pipe, the contribution in U is very less, 2.5 into 10 raised to minus 4. And again, the contribution of the inner heat transfer coefficient is also less. So the main determining factor here is convective loss to the environment. This is 34 times higher than the convective heat transfer from inner fluid to the pipe inner diameter. So this has to be checked. So maximum heat transfer is taking place because of the this bare pipe, we can say, the heat transfer coefficient because of the outer. So outer heat loss is the major thing. That's why many times in engineering applications, the hot fluid pipes are insulated to avoid the heat loss. Okay, so this is the next problem. So this is the extension of the above problem. In this problem, the pipe is bare. It is not having insulation. Now extension of the problem reads like it has a insulation. In the above problem, now the pipe is covered with a layer of asbestos. Also the thermal conductivity of asbestos is given as 0.18 and all other parameters remain the same. So again we will apply this. Now here they ask that what will be the rate of heat transfer. Here it should be the heat transfer. So what will be the rate of heat transfer with insulation thickness of 0.5 mm first and then 10 mm. So we have to determine rate of heat transfer in two cases where R3. So R1 is known, R2 is known. Now R3, first case R3, in the first case is say 0.5. So 14.5 plus 0.5. So and in the second case, when the insulation is 10 mm, in the second case it is 14.5 plus 10 mm, that is 24.5. So in two cases we have to calculate. Now everything is indicated in these notations here, and then if you just apply those equations, substitute the values here, you will get UO with 0.5 mm of insulation, the overall heat transfer coefficient to be 9.64 watt per meter square. Now when the insulation thickness is increased to 10 mm, the overall heat transfer coefficient has naturally to be less, so it is 1.86. So if the thickness of the insulation goes on increasing, the rate of heat transfer also goes on increasing. So the heat transfer rate will decrease with addition of insulation from 0.5 to 10 mm thickness. Now just out of interest, critical thickness of insulation, if we calculate, which is the ratio of thermal conductivity of the insulation by outer convective heat transfer coefficient. So 0.18 is the thermal conductivity of the insulation and 12 is HO, that is convective heat transfer coefficient outside. So this ratio comes out to be 0.015. So 15 mm. Now what is 15 mm? 15 mm is RO. So this comes out to be, this is a 15 mm. Okay, so we can say this dimension comes out to be 15 mm. This is called critical radius of insulation. What will happen at the critical radius of insulation? See, the heat transfer will go on decreasing as you go on adding the insulation. Now sometimes heat transfer goes on increasing. So till 15 mm heat transfer will go on increasing till 15. At 15 mm thickness, we have seen here. At 15 mm thickness, 0.5 mm of insulation thickness, 15 mm radius, heat transfer is maximum 9.64, and then further it goes on decreasing. So if you want to use this, you want to insulate this pipe, the minimum thickness you have to provide is 15 mm, and beyond that if you go, the rate of heat transfer will go on decreasing. In case of electrical insulator, suppose this is a electric wire, copper wire. Now in case of copper wire, you want to dissipate the heat generated by electricity. In that case, the heat transfer rate has to be maximum. So in that case, the thickness of the insulation provided is the critical insulation of thickness. So if you provide the radius of the insulation, plastic insulation over a wire, which is more than the critical rate of radius of insulation, then less heat will be dissipated, and that will go on accumulating in the wire, and the wire will be overheated. So particularly this critical radius of insulation concept is important in electrical engineering point of view. Now this is the last problem, problem number 7. Air at 120 degrees Celsius in a thin stainless steel tube is flowing. So air at 120 degrees Celsius is flowing through a thin walled stainless steel tube with H equal to 65 watt per meter square. So HI is given. The inside diameter of the tube is 2.5 and the wall thickness is 0.4 mm. Now 18 thermal conductivity of the pipe material is 18 watt per meter Kelvin and the tube is exposed to an environment with HO 6.5 watt per meter square Kelvin and ambient temperature is given as 15 degrees Celsius. So we have to calculate the overall heat transfer coefficient and the heat loss per meter length. Now what thickness of an insulation having Ki thermal conductivity 40 milliwatt. Now this is milliwatt per meter Kelvin should be added. So milliwatt means 40 into 10 raised to minus 3 watt per meter Kelvin is the thermal conductivity. So this how much insulation must be added to reduce the heat loss by 90%. So we want to reduce the heat loss by 90%. How much insulation has to be added? Now this shows the arrangement. So this is a pipe. So now we have to calculate first the heat transfer without insulation. So if you calculate rate of heat transfer without insulation with all these equations and all these parameters, if you substitute parameters here, only pipe and outer heat transfer coefficient. So no insulation is added here. So R2 and R1 only pipe and Kp. So if you substitute here, the overall heat transfer coefficient comes out to be 6.5 watt per meter square Kelvin without insulation. So with this UO, if you calculate heat transfer rate without insulation, with heat transfer rate without insulation, if you calculate, it comes out to be 55.28. Okay. Now, if heat transfer rate with insulation and having Ki equal to 40 into 10 raised to minus 3, what will happen? So why we are adding insulation here? This heat transfer, now this heat transfer rate, current heat transfer rate has to be reduced by 90%. So I reduce this by 90%, so 10%. So the desired rate of heat transfer is 10% of the current value, that is 5.52. So 10% of this is 5.52 watt. Now substituting Q equal to 5.52 in the above equation and obtain the value of new value of overall heat transfer coefficient, that is UO1. Then substitute this value in the expression of UO with the unknown value of R3. So we will seek outer diameter of the insulation. Then thickness of the thickness of that 90% reduction, thickness of that insulation ensures 90% reduction in the heat transfer. So if you equate this to be 5.52, you will get the modified overall heat transfer coefficient to be 0.65 watt per meter square. So now this is known to you. So if now here insulation is added in addition to pipe insulation. So please note the difference between this expression and this expression. Here there is no insulation added, only pipe. Here there is insulation added with radius R3 by R2. Okay, and with Ki, thermal conductivity of insulation, and HO is already given. So if you substitute all the values, you will get R3 to be 25.65 mm. So the thickness of the insulation that must be added is 12.75 mm. So I hope these three problems will get you a sufficient idea of combined conduction convection heat transfer cases. We will continue our discussion with radiation heat transfer and combined convection and radiation heat transfer, which will be helpful for solar flat plate collector analysis.